This applies to covalent or molecular compounds. So basically what's going to happen is you're going to be able to look at a structure and determine whether or not a compound is actually polar or not. So, in order to be polar, overall, two criteria must be met. Two criteria must be met. The first one is the molecule contains polar covalent bonds. So the molecule must contain polar covalent bonds, and 2, a net dipole is present. So a net dipole is what you get when you add up all the dipoles. Four from carbon, 6 from each oxygen for a total of 12, so we have 16. Carbon must make 4 bonds. We've used up 8, we have 8 left. 4 on each oxygen. Okay, carbon-hydrogen, the difference in electronegativity is 0. Nope, sorry, 0.4. Therefore, non-polar, I should write that out so you guys, non-polar molecule. There's no dipoles, therefore it's non-polar. NH3. You looked at the difference in electronegativity. You determined there were dipoles. So we put them on. CO2. There's definitely a difference in electronegativity. So you put them on. Now, in order to figure out if you have a net dipole, you have to add these dipoles as vectors. So if you haven't done this in physics, you need to pay closer attention. If you have done this in physics, I suggest you listen to be courteous to others. So, you've got a head and a tail for vectors. Okay, any questions?
If we use like the squiggly thingies, how would this work?
You wouldn't be able to do that.
Okay.
Yeah. This is why I prefer this way. Okay. Do you want to ask? 1 and 2. Okay, Johnson.
Yes.
Which one do you want to start with?
1.
Okay. So if we start with 1, here's our start. We're going to go in this direction. Then we're going to place number 2 goes equal length, opposite direction. So they're basically on top of each other because they're equal in difference. They're both 1.0 and they're opposite in direction. So do we end up at the same place we started?
Yes.
So there's no net dipole. No net dipole. Non-polar molecule. So on this page, we have a structure without dipoles that's nonpolar. We have a structure with polar covalent bonds that is polar. And we have a structure that's got polar covalent bonds and is nonpolar. So, because the dipoles cancel, there's no net dipole, it's nonpolar. There is a net dipole, it's polar. On a nice arrow, this is the head, this is the tail. You're going to pick any one of your dipoles to be your first vector. It doesn't matter which one you pick as long as you only use it one time. And what you do is you lay it down on your paper, and then you take the second dipole and you add it to this one. But you add the tail of the second vector to the head of the first one. So if I have another vector, maybe it goes this way. So the tail of my second vector attaches to the head of the first vector. And then, if I only have two vectors here, you've got to see, here's my starting position. Did I end up at the same position where I started? I did not, because I finished up over here. Therefore, I have a net dipole or a resultant dipole. Your resultant or your net dipole has a tail and a head. The tail is at the start. The head is at the end. So where your last vector finished is the head of your resultant or your net dipole. If you end up with a net dipole, you are a polar molecule. If you have no net dipole, you are non-polar molecule. So you have to pay attention here because you can have polar covalent bonds and be nonpolar because you don't end up with a net dipole. You would have a net dipole. Who has the strongest pull, phosphorus or chlorine? Phosphorus. Sure? Chlorine, sure? So chlorine. So you would end up with a net dipole in this direction. Because these two on the side would cancel. They're equal in opposite directions. How about this one? Which direction will the net dipole go? Up or down? Up. Yeah. Your net dipole will go in this direction. HCl, which direction will the net dipole go? Left or right? Net dipole. How about the one at the right? N2, H2. Which direction will the net dipole go? Up or down? Up. Net dipole. Does it have to be accurate? Bond angles? No. Just, I know that for the N2H2, I've got a dipole going up along one HN bond, another one going the opposite direction, but they're both on an angle, so my net dipole is here. Okay? All right.